Okay, so it's a slightly enigmatic title, and I'll try and explain what it's all about. Firstly, the major problem of the Western world is now the pandemic of obesity, and this is the disease control figures that came out last year, and nobody tried to suppress them. When they tried to bring out some figures on gun control, they were told that they weren't allowed to. But for obesity, it is allowed, in spite of the very large food industry's many complaints. But in America, a third are obese. In the UK, the numbers are actually, unfortunately, beginning to allied. So we're not much better than the Americans. The problem is the diseases that follow. And there's, in the UK, about 100 excess deaths a day from obesity. That's a pretty serious number. So it is now the biggest pandemic the world has ever seen. And things like diabetes, something about 2/3 of diabetes is due directly to obesity, and the rest is influenced by it. So it's not at all good news. Alzheimer's disease has increased. People get lower salaries. Suicide rates are higher. NAFLA, fatty liver disease, giving rise to cirrhosis. And, of course, ordinary things like arthritis, etc. So it's a very serious problem. And we've attempted to do something about it, or at least the pharmaceutical industry has. And there's been a massive list of failures. Here is a long list, things like rimonabant, which was licensed in Europe and made everyone depressed, and after a few suicides was withdrawn. They've rather forgot that although you do indeed get the munchies when you smoke cannabis, as you know, actually blocking the cannabinoid receptor does the opposite of smoking pot, which makes you therefore miserable. So you had half of Europe getting very miserable. It wasn't entirely due to Brexit. So what has worked? Well, sort of. Orlistat. People have put on it. About 1% of them are still taking it at the end of a year. Increased laundry bills, something called oily leakage, loss of friends, rather large tablets. No, it's not really a winner. Lorcaserin, which is the 5-HT agent. They tried to get rid of the side effects of fen-phen, which caused heart disease, but they've made it so feeble it hardly produces any weight loss. Topiramate and phentermine, topiramate is a sulfated glucose. That works very well, but it's got an immense number of side effects. For example, loss of concentration, which is really quite a serious thing. And so people, again, don't take it. And the company producing it has gone bankrupt once and is looking as if it's going to go bankrupt again. Naltrexone, bupropion, equally not very effective. The one that is good is Saxenda, liraglutide 3 milligrams, the high dose. And that does work. But the thing that really works, the thing that works very well, is, of course, Roux-en-Y bypass. And the figures, which are now getting fairly long in the tooth, but they were still very big surveys and very long-term follow-up, one from Europe, one from the USA, demonstrated very good outcomes in the long term. You actually live longer after Roux-en-Y bypass, which is always a good test of whether a treatment is working. And the interesting thing was that cancer had previously been known to be much higher in the obese, and nobody quite knew why. But its connection is demonstrated very well by the fact that when you lose weight, your cancer rates fall dramatically. And it's now obesity that is a bigger cause of cancer than is cigarette smoking. Unfortunately, bariatric surgery is expensive. There's a significant death rate. I've just come back from the Imperial College Diabetes Center in Abu Dhabi, and I met the bariatric administrator for the Cleveland Clinic there, and he said almost all his work was rectifying errors that overbold surgeons doing Roux-en-Y bypass not very well had caused the local population. So it is pretty dangerous. In unskilled hands, the death rate is over 1%. In the published series, which is obviously the people that really know what they're doing, it's under 0.5%, but it's still quite significant. There's a readmission to hospital rate of approaching 50%. Again, published figures are slightly better, but then that's the major centers that really know what they're doing. And the most difficult thing is that it only produces good weight loss in about 2/3. Surgeons do a fairly conservative bypass in order to avoid the death rate, and therefore about 1/3 don't lose enough weight, and you can't adjust it, so it's a one-off go. The good effects on health are entirely proportional to the weight loss achieved. There doesn't seem to be any magic sauce, at least as far as I'm concerned, looking at the figures. And we think it works through release of gut hormones, satiety gut hormones. Now, it's my jubilee, because nearly 50 years ago, I came down to a British Biochemical Society meeting in Brighton, and there I met a Swede called Victor Mutt, and he had just isolated a gut hormone from pig guts called secretin. And he was a very egalitarian person. It helped that his background was from Latvia, he was a refugee, and my background is also from Estonia and Latvia. So that meant that we had a little thing in common, so he gave me 2 milligrams of the entire world supply of secretin, which was about 2.9 milligrams. Now, for him to do that for a junior scientist in the UK was frankly quite amazing. Anyway, it got me started because I was able to use that to immunize and set up a radioimmunoassay, then the cutting-edge technology to measure blood secretin, and we went on to work with him over the years. He's now passed away, unfortunately, and we got many other biologically active peptides from the gut, and those often turned out to be hormones. So this is a list of hormones. The ones in bold are the ones that affect appetite, and therefore are perhaps of particular interest. But the endocrinology of the gut has not been particularly well studied by endocrinologists. And one of the reasons is they're not gathered together in glands. The endocrine cells in the gut are the diffuse endocrine system, producing an integrated signal. The more food you eat, the bigger the release of hormones, because the greater the length of gut that's stimulated. Also, they're released not just by the luminal content, but also by the innervation. So the submucous plexus of nerves is very important in regulating gut hormone release. And the late Mohammed Gharti and I studied the effect of psychological evidence of food and showed that you got quite a reasonable gut hormone release with the sight of food, the smell of food, etc., nothing in the lumen at all. So the innervation is very critical. As you can see, the endocrine cells are fairly typical. On an electron microscope, you can see the stored granules, which are ready for release. There's a little microvilli, which does reach the lumen, so it can sense the lumen. And we used an original technique of immunocytochemistry, shown in the bottom there, staining with antibodies, so we could show that these biologically active peptides that Victor Mutt managed to extract from the gut and showed they did things to smooth muscle. We were able to show, myself and Professor Julia Polak, the late Professor Polak, Dame Polak, that they could stain endocrine cells. With our radioimmunoassay, we showed the release into the bloodstream. We then went ahead and infused them to mimic the levels you see after meals and showed they did things. Actually, initially, we were only interested in the digestive system, so we showed they did things like switch off gastric acid. It was only later that we realized that they were doing far more than controlling digestion. Here you can see the administration of an antagonist. Now, when an antagonist does something, it suggests that the agonism is part of physiology. And this antagonist to GLP-1 caused an increase of food intake in otherwise satiated rats. And that demonstrated that part of that satiation was the release of GLP-1 from gut endocrine cells. And we published all these things in a series of papers. In particular, we infused something called GLP-1, glucagon-like peptide 1, into humans for the first time and demonstrated quite a good insulin release. And that's become, of course, one of the major medications in diabetes. So there are three types of action of a gut hormone. Firstly, after a meal, it helps switch off your appetite, so it's the reason you don't feel so hungry after lunch. Secondly, when it's chronically elevated, as in a gut disease, as in pancreatic exocrine failure, or short bowel syndrome, or tropical sprue, or celiac disease, the gut hormone release is considerably increased. We, in fact, surveyed the International Congress of Gastroenterology when it came to London, and we were able to demonstrate that those people that ate injudiciously and then got conference diarrhea, hope no one's suffering, had very high levels of gut hormones, and as soon as they came down, their appetite returned. So there was a very close correlation in the loss of appetite. So infections in the gut also release the gut hormones. In fact, it's the physiological way that the gut has of saying, hey, I can't cope with any more food, please stop eating. So it's signaling directly to the brain. And finally, in the extreme circumstance of very high gut hormones, that produces negative food intake, otherwise known as vomiting, and it's part of the emergency system to get rid of something inappropriate. Now, when you use a single agent to try and control things, you often get side effects because you have to give it in rather high doses. And the GLP-1 administration to diabetics is in that category. And therefore, the limiting fact is that nausea that I said is a physiological effect of the gut hormones. So that high-dose GLP-1 analog, the one produced by Novo Nordisk, is known as liraglutide because it's got a lipid side chain, which means you only have to give it once a day, Victoza. And that produces, in its initial administration, a high level of vomiting and nausea, so you have to start with a low dose and build it up. And if you want to have the maximum effect on weight reduction, the now marketed Saxenda, which works very well, you have to give the maximum dose that's tolerated, and you do end up with about 2 to 3% nausea. So at the very high dose, there is a constant slight increase of symptoms, and they really couldn't go any higher. And that produces a reasonable weight loss of about 6 kilograms, which is actually quite clinically helpful, and it's totally safe. But that isn't quite going to make your door-stopping large guy look any better. It'll produce a, ooh, yes, I see you've lost some weight from the physician, but the patient really hasn't had to change their clothes or do anything very dramatic, and they don't regard this as actually an effective treatment. Of course, we're now disliking daily injections and moving to weekly injections. And dulaglutide is 2 GLP-1s attached to the IgG4 Fc fragment, which binds to various things and prolongs its action in the bloodstream. Unfortunately, it stops it getting across the blood-brain barrier. So the weight loss that you get with this agent isn't very good. And it just points out that it's really necessary that if you're going to behave like a natural gut hormone, you have to penetrate to the appetite centers in the brain, the median eminence, etc. Now, we started working with Oxyntomodulin. Its name is a bit confusing. It was initially discovered as something which switched off acid. Acid comes from the oxyntic cells in the stomach. So it modulated the oxyntic cells, thus the name Oxyntomodulin. Its structure is also a bit confusing because actually it's glucagon, but it's glucagon with a tail. And the tail stops it having an effect on blood glucose. So unlike glucagon, when you inject Oxyntomodulin, you don't get a rise of blood glucose. And that tail obviously does something else. It is, of course, a post-translational enzymic processing difference. So the Oxyntomodulin is produced in the gut, but pancreatic glucagon is produced by the alpha cells, but the pre-pro hormone is the same, the messenger RNA is the same. It's just the enzymic processing differs between the alpha cell in the pancreas, in the islet, and that in the gut endocrine cell. Button problems. There we are. Now, this was the finding that we made at the beginning of the 2000s, in the noughties, 2002, which was that when we did a paired feeding study, we got a rather surprising result. So these are growing rats, and we're injecting them daily with oxyntomodulin to see what effect it has on appetite and weight. And we were able to demonstrate that the animals did not put on fat. So here's the oxyntomodulin group, and while they're growing normally, they've got very little fat reserve. When we had a pair-fed group, given the same lesser amount of food that the oxyntomodulin group ate, rather surprisingly, they still put on quite a bit of fat. So what was the difference? We speculated it might be due to an increase of energy expenditure. So obesity is a balance between energy expenditure and food in. And if the food in hasn't changed enough, maybe it's the energy expenditure difference. So, being bold, and this was before the European Clinical Trials Directive, which would make this action illegal, we set up our own clinical trial. Because we had no money, we pinched the syringes from the ward, and we gave for 4 weeks a double-blind. We had a proper control committee, and it was all done double-blind. And actually, the patients couldn't tell us whether they were on the oxyntomodulin or on the saline injections. They took them 3 times a day. And as you can see, we gave everybody dietary advice. So the controls, when the computer program finally told us who were the controls and who weren't, they're in the bottom in green, lost a little weight due to the fact that we were giving them dietary advice. But the weight loss on oxyntomodulin was truly impressive, getting close to the same as you see after the Roux-en-Y bypass. And this was without any symptoms. So the people were going to work, they were at home, they didn't have any problems. So it meant that oxyntomodulin looked quite a promising therapy. We were interested, obviously, in that energy expenditure increase. So we did a second trial, and this time we had 2 ways of measuring energy: the basal metabolic rate, which is oxygen consumption at rest, so that's the oxygen hood, and also biological activity, voluntary movement, and there we had an early version of what you now would say was your smartwatch, which tells you how much movement you've done every day, and this recorded for 3 days how much movement in the X, Y, and Z dimensions, but also heart rate. So if you stood on a bus and just got jogged up and down, that didn't count because the heart rate didn't go up. And because that's not a direct measure of exercise, we had everyone as their own control. So it was a crossover study. And we were able to demonstrate that when people were on the oxyntomodulin, and this was again double-blind and they didn't know which they were on, they had a 20%, 26% increase of movement. And when one worked all that out, you can see they also ate less as before. So in this repeat study, we got the same results on food intake. That amounted to a 9% extra use of energy or loss of energy. So that was why the weight loss was so good. So oxyntomodulin in humans did behave as it does in rats. Now, oxyntomodulin has 2 components in it. It has a component which fits the glucagon receptor, and a component which fits the glucagon-like peptide-1 receptor. And the question is, could you explain the whole of the effect of oxyntomodulin by doubling up on those 2 agents separately? Or was there some special oxyntomodulin receptor? So together with my colleague, Professor Tricia Tan, we did a lot of infusion experiments in human volunteers, giving mixtures of glucagon and GLP-1 and the 2 separately. And we measured energy expenditure, here the basal metabolic rate. And as you can see, it goes up with glucagon, as we expect. So they're the controls, there's the glucagon. And the addition of the GLP-1 didn't make any difference. So it didn't obviate the energy expenditure increase of glucagon. And here you can see the glucose tolerance. And obviously, glucagon puts up glucose. But when you've got a combination, it does the opposite. And as you can see here, the combination actually had the lowest level of glucose at the end of the study. So both glucagon and GLP-1 decrease appetite. Glucagon increases energy expenditure, And GLP-1, by releasing insulin, this is speculation, we think blocks gluconeogenesis. So insulin wins on the liver. While glucagon puts up glucose, insulin blocks that, and the block wins. Obviously, you do need some functional beta cells for that to work, and there was a series of publications listing various of my colleagues who actually did all the work. One of the advantages of getting old is you don't need to work anymore. So another gut hormone is PYY, and there you can see the sequence. It's part of a neurotransmitter family. NPY is a neurotransmitter in the brain. PYY is a peripherally released peptide, and they're evolving apart. They have some sequence differences, but they're clearly virtually identical. The active sequence is identical. And so we studied this and found that it did indeed decrease appetite. Here you can see that it's released depending on the size of the meal. The bigger the level of PYY in the circulation. And this is the reduction of food intake. Now, we had two groups, lean and obese. And my colleague, Rachel Batteram, was the lead on this particular study. And the point about the obese group is that leptin had recently been discovered. And as you know, leptin has been trialed for the treatment of obesity. It's the agent released from fat which switches off appetite in rodents. But when it was given to humans in pretty massive doses, it did absolutely nothing. Well, that's not quite right. The patients complained of the sore injection sites, but their weight didn't change. And that, of course, tells us something fundamental about the obese. They already have very high leptin levels. And we now know that leptin is, in fact, a hormone of absence. If you don't have leptin, your periods will stop, your growth will stop, and your immune system switches off. And in fact, that's the reason why following famine comes plague. And across the history of mankind, that's been a major problem. And that's because your immune system uses a lot of energy, and it gets closed down when you're critically short of food, when you have no leptin. So leptin doesn't seem to do anything, but if you don't have it, it's really serious. And rather interestingly, there's a peptide released from the stomach called the hunger hormone, ghrelin. And when we infuse ghrelin, everybody eats more. And the body actually has a way of coordinating all this. So during a PYY infusion, your ghrelin levels fall. Actually, this ghrelin level seen here doesn't look very dramatic, but a lot of the ghrelin is biologically inactive circulating material. And so the fall of the biologically active form is really big. It almost disappears. And what was very interesting in these series of studies was looking at the saline control in the obese and the lean. And the saline control day, which obviously wasn't affecting the hormones, showed that PYY was much lower in the obese. In other words, the obese have an absence of this satiety hormone release. It's not surprising that once you become obese, it's very difficult to lose weight. You don't have the same satiety signals. So in a sense, if you treat the obese with PYY, you're putting back something that they're actually missing. Now, we've already mentioned that Roux-en-Y is a really effective treatment. So if you've got a medical problem, call for a surgeon. He'll put it right for you. Surgical changing of the metabolic rate is obviously important. And as you can see here, the PYY levels go up dramatically after the Roux-en-Y bypass. And it's, we think, the reason why the Roux-en-Y bypass works. It tells the gut that there's malabsorption. That produces the release of satiety signals to the brain, and you don't eat as much. It was first invented because it was thought to produce malabsorption. It does not produce malabsorption, but what it does do is tell the brain not to eat too much because the gut can't take it. And it's obvious, really, that if you have more than one hormone, you have a much better effect. So here we've got combination of Oxyntomodulin and PYY, and that demonstrates that together they're much more effective, and that the attempt to give just one of them, as in the case of Saxenda, is not going to be very effective. Okay, well, when you infuse gut hormones, does it have the same effect in the brain as does eating food? So here is a blood oxygen level dependent functional MRI analysis of the brain of volunteers in a meal. This is the effect of eating food. This is the effect of infusing gut hormones, and the two are indistinguishable, suggesting that we really are having a physiological effect on the appetite centers and the CNS. So conclusions are that the only way to prevent and treat type 2 diabetes may be the Roux-en-Y bypass. All those drugs you're giving may be a mistake. The single major mediator, we think, is an elevation of satiety gut hormones. And so the next question is, could we have a medical bypass whereby you give the gut hormones, a sort of super Saxenda, in such a way as to control people's appetite in a way that you could adjust to individuals? Now, the problem is that most hormones fall apart very quickly. They have a half-life of about 5 minutes. And they're designed like that because if you're going to control something, you've got to be able to switch off the release and have the person hungry again. So you can't have the hormones hanging about. They're designed to fall apart in the circulation. Now, if we want to use them therapeutically, that's bad news. And actually, people don't like injections. So a once-a-week injection is just about acceptable. It has to be painless. There mustn't be any side effects. And it's obviously got to cross the blood-brain barrier. So in making it last a week, you can't attach large things to it. So that was the challenge that we set ourselves in what we set up as a drug therapeutic group. And it isn't as simple as it first sounds. We're all taught that the lock and key idea of a hormone fitting a slot in a receptor and turning things on, but it couldn't be more complicated. So structure-activity relationships that people have studied don't work. No one has managed to predict a good ligand to fit a receptor. All of that in silico research gets nowhere. They're very good after the event. And that's because the molecules are jigging in all sorts of different shapes. They spend microseconds in particular shapes. It's difficult to identify what the receptor will actually look like in vivo. And they're quantum effects, like quantum tunneling. Our computer programs don't do anything about. But if you do a deuterium hydrogen exchange, you can see that they're important. Anyway, we've got allosteric effects, like here, where you can see that well away from the active site, small changes make an enormous difference. And we now know that the extracellular part has to fold over. And that's an allosteric effect, an effect at a distance. And that's regulatable. We also know that there are other things in membranes which attach to D protein receptors and make them different. First discovered as the receptor activating modifying protein 1, which turned the CGRP receptor into a calcitonin receptor-like receptor, etc. And there's a ramp which fits the glucagon receptor. And when the ramp hits the glucagon receptor, things change. So Jamie Segler has done the research, PhD student in my lab. As you can see, we've got staining here of different things. There's the ramp, and this is ramp overexpressing cells. There's the receptor, and the two coexist to some extent. But much more important here, in the presence of the ramp, we don't get the same effects at all of the glucagon. So it really has a big influence on the biological activity. And of course, the ramp's only expressed in certain cells, so that's why certain cells get affected differently from other cells. And it's beta-arrestin, first identified as arresting the effect of the beta-adrenergic receptor, so it switches it off, and that's very different in the cellular signaling system from the classical cyclic AMP, and it tends to switch off the effect on insulin. And here we can see with Exendin, if we switch from histidine to phenylalanine at the bit that fits into the receptor, we can or not affect the receptor differently. So here's an effect of the Exendin with a Phe1 as opposed to histidine 1. And as you can see, there's a big difference in the effect. And here we can see that with the Phe1, the receptors are remaining on the cell surface, whereas with ordinary Exendin, they rapidly internalize and become inactivated. The functional result of that is seen here, that after 8 hours, you have almost no effect on glucose of exendin, but the Phe1 exendin is still very active and is releasing a lot of insulin. So this really matters. Okay, so looking at a number of analogues together, we can cure diabetic mice. So here's our analogues in combination, and their glucose has become completely normal. That's the best we can do with GLP-1, and they're still diabetic. The weight loss is considerable, but the loss of appetite is very small, so there's not much nausea type effect. Now, once a week, we had to make long-acting analogues. So here's a 10-day single injection, elevated blood level of a PYY agent and an Oxyntomodulin agent. So this is our drug discovery team. This is what the agents look like. They're really cheap to make. So Saxenda is pretty expensive. These will be very cheap. This is our current plan, developing the combination. We've raised the funds to do all this. So we're in phase 1 clinical trials now. We did a quick calculation. There's about 3 billion obese people. There's no current medication to compete with. We think about 1 billion can afford us. We think we'll perhaps sell to about 5%. That would be the market price. This is the profit. We had George Osborne visit us, and he was very impressed. And of course, it's a way of altering your basic drives. So when you haven't eaten for a bit, like 3 or 4 days, turn to your neighbor and look at them. They become just a source of food. You would love to eat them. You get so hungry. And that's an absolutely basic, overwhelming drive to eat. And we can switch it off with these hormones. So it's kind of dangerous. Thank you.
Thank you, Steve, for taking us through the wonderful journey of gut hormones, and hopefully we look forward to this medical bypass therapy, you know, and obviously making lots of money, of course. So it is a great pleasure that I hand over to you the Jubilee Medal today.
Thank you, Barbara.